All right. Afternoon, everybody. Thanks for joining in. We have more of a tutorial today on a topic that I think we touched on a couple of years ago, but it's been a while. So Michael Sinatra was gracious enough to give us a little bit of his time to go through a tutorial on how to use Traceroute, and this is based on some material that has been presented at NANOGs and other events before. So I will turn it over to Michael to get us started.
Thanks a lot. Um, I did take some of the material from Richard Steenbergen, or Raz, as people call him, and his tutorial that he gave in Nanog. But I also figured since that's already available online, I'll just make that a prerequisite for this. So what I'm going to do is kind of jump off from that and look at a few cases where particularly the way we run RNE networks nowadays tends to interact with Traceroute and Tracepath and other trace tools in ways that are kind of complicated and make inferences about those networks and about network performance and other things a little bit more challenging. So I'm taking some specific examples out of the uh, really great tutorial that Raz does, and I hope that you had a chance to look at it or at least go through all the slides in the slide deck. And I'm going to pull out some of those and then continue launching off of a whole bunch of tangents from there. So as you can see, if you see the format that's over there on the right, that means that's actually Raz's material and credit where credit is due there. He also has a great quote. The quote up top kind of matches the quote. The quote at the bottom is kind of the TLDR of the quote at the top, which is really a lot of network engineers. And I thought this is kind of harsh, but a lot of network engineers, according to Raz, don't have quite as much of ability or not much experience to really be able to make inferences about what Traceroute is trying to tell them, and instead kind of make maybe the wrong inferences. And so I'm going to try to come up with maybe something a little bit better than that. Part of the inspiration that I'm coming from too is a quote that was about 20 years old from Roger Hess, who's now passed away. He was quoting some people in the high energy physics community as saying that routers are slower than FedEx. They were talking about the real Federal Express, not the data transfer tool. And my immediate reaction to that 20 years ago was, do they even understand how like routers work or how what the architecture is of a modern internet router, modern 2005 internet router? And are they interpreting traceroute correctly? Are they looking at those round trip numbers as though they're real latency numbers? So even 20 years ago, and I would say even 30 years ago, routers did not provide the level of latency information that, I should say, traceroute interacting with the routers did not provide the level of latency information that we needed. Another motivation is that I've designed a network that creates trace routes to look like this, and I should probably owe it to you to tell you a little bit about what all that means. So I kind of like want people to understand that the level of complexity that is in modern RNA networks today requires a little bit of understanding of what traceroute is telling you and also what it's not telling you. And from Mrs. Marion, my sixth and eighth grade English teacher, who also taught me how to speak. She was one of the people who pointed out that wisdom is really knowing how much you don't know. So I'm going to try to impart wisdom today, in other words, lack of knowledge, to you as well. So let's get started. Um, I talked a little bit about this. Uh, it's not so much that traceroute itself is lying, but it's a hack. And trying to understand how that hack interacts with sort of older networks versus newer networks is something that our understanding of it and our documentation around it needs to evolve as well. And so the whole idea of traceroute is that it takes advantage of RFC 1812. What RFC 1812 basically says is that if you're a router and you get a packet that's expired, you have to drop it and send back an ICMP message. It's sort of like saying to my mom, this food's expired in the fridge, you have to throw it away. And you can't do the old, oh, it's probably be good for, another couple days. We'll put on the grill this weekend. Routers can't do that. They have to throw the packet away. So you can take advantage of that by using traceroute to create a very low TTL, get it to expire, and then increment the TTL by one, get it to expire one more hop down the path, and continue. And you can actually suss out what the path is by looking at those ICMP messages that come back. You can also calculate the round trip time of that, but it's important to understand that's not a latency calculation per se. That is a sum of a whole bunch of things. If you think about it this way, it's kind of like if you're trying to measure the length of a football field and you do it by walking around the perimeter of the stadium outside of it, yeah, there's a little bit of the, football field component that's in that measurement that you did, but you're not actually measuring the football field. You're doing something else that has the football field as a component. If the football field triples in size, that's going to definitely be noticeable as you walk around the much bigger stadium. But there could be other reasons that are causing that stadium to get bigger or smaller, not necessarily the football field. Um, and one of the things that Raz says at the end here is RC1812 says that ICMP must be sourced from the egress interface, but that's not what Traceroute actually relies on. It actually relies on it being sourced from the ingress interface. But there is an exception to that rule, which I will show you later. So let's look at history. Yeah, Wikipedia says that it was written in 1987. The source code that I've seen still has a 1988 date plus a whole bunch of commentary by Van Jacobson, which is really hilarious. And so I would actually refer you to that. And I do have that as a reference at the end of this presentation. But one of the things I also want to do is he gives a little credit where credit is due. And since a lot of us know Guy Alms and Matt Mathis, that might be that might be familiar to people here. So I just decided to throw that comment in there. So 1987-88, what did networks look like in 1987-88? This is the UC Berkeley network in March of 1987. This is frightening for a lot of network engineers because all of those boxes, those are all computers. They're all linking networks together using computers. In most cases, those are VAXs. So you have a lot of VAXs that have multiple interfaces on them, and they're running BSD 4.3 BSD Unix, and they are, running route D and routing between those networks. The one dedicated router, it's actually a cluster of routers over here. It's a Proteon. Those were also software-based, entirely software-based routers. Proteon did have a hardware accelerator, but it was for token ring. And these are all Ethernets here. Most of the circles are 10 megabit Ethernet. So you've got a whole bunch of 10 megabit Ethernet, probably thicknet. In most of these cases, I know for a fact the 144 CCAM network there down here that was being routed by an IBM PC-RT, which is the predecessor of an RS-6000. I know for a fact that was mostly thicknet. So this is what I looked like in 1987. Yeah, I don't look like that anymore, and neither do networks. So we don't have VAX 11750s doing all of our routing. We have very modern ASIC-based and hardware and FPGA-based routers. Those work very differently than VAXs do. And the inferences we can make as we send a packet through a modern ASIC router, or if we send a packet that expires through a modern ASIC-based router, is very different than we would from a VAX 11750. In addition, networks have evolved to make extensive use of MPLS. They also make extensive use of ECMP. If you look at whoever designed this or looked at this map, there's no ECMP here. They'd be bewildered by ECMP. They'd be thinking like, why don't we just increase the links? I mean, why would we do ECMP? And we also make extensive use of L3VPNs. Again, that would be weird. We did all this work to connect these networks together, and now you're putting, now you're trying to make them physically connected but logically separated. That doesn't make any sense. Why would you do that? Well, there are a lot of reasons why you would do that. And so the question is, the way Traceroute still works, but the way we interpret it needs to change, and the way that we document it and the way we understand it needs to change. So has our understanding changed? I want you, if you're on a Mac right now, I want you to go ahead and type man traceroute, go open a terminal window, go type man traceroute, and look at what it says. You're going to get the original, and I'm running Mac OS, ironically 26.5.1 Tahoe. You're going to get the original man page for 4.3 BSD Tahoe, which was only 38 years before the current version of Tahoe. So essentially, this example is given here. And one of the things I want to tell you, there are sort of two things I want to tell you about here. One is that UC Berkeley is providing transit between LBL and the NSF net, which is how you get to MIT from here. So you're tracing to MIT from LBL and you're going to Berkeley. You're also going through some faxes at Berkeley to get there. So, for example, Lilac is the first one you go through. That's an old name for Berkeley fax. There's Lilac, and it eventually hits this. There's a couple of things that have changed between that traceroute example and this actual map, but basically you end up going into the computer center network, which is 128.32.136, and that .23 is the gateway. That was the gateway address well into the 2000s for that particular network. And then that goes to that cluster of proteons that I was talking about before. Then it finally goes out of Berkeley and onto NSFNet. So basically, there's the proteon cluster, and that's basically what happened in this old trace route. So it actually matches this old 1987 map. That was kind of cool. And by the way, I collect maps like this. So if anyone has cool maps that are old from like the 80s and 90s from their early 90s from their campuses, feel free to ms at es.net. There's also a lot of newer tools that are out there now that do different types of visualization and other things like that. I'm going to go through these really quickly because I'm going to provide examples from them later. So which tool do you use? Well, depends on what you need to do. I mean, do you need IPv6? So of course you need IPv6 for it. Are you using MPLS? Probably. Are you using ECMP? Probably. Are you trying to see if there's asymmetry? Do you want to know path MTU? Do you want the output to actually be readable or really messy? Do you want it to be readable by a human or by a machine? A lot of these tools now provide JSON output. Do you want it to be readable by a scientist? Okay, I'm just kidding about that. And do you care what language it's written in? That actually does make a difference. If it's written in a modern language like Golang or Rust, it's going to be more portable. That's what I've noticed. And a lot of those languages have really good libraries to the sockets APIs of different platforms. So they're able to be able to run on a variety of platforms and operating systems and stuff. Do you also want it to be in the native package repo because you don't want to have to futz around with other repos, or your sysadmins don't want to have to futz around with other repos, or your security people don't want to have to futz around with other supply chains? Those are all good things to take into consideration, which we'll talk about kind of at the end. Okay, when we get back to Traceroute, it's in our best interest to have accurate information. So one of the things that Traceroute really does is it relies on the network operator's ability and effort, and in some cases level of automation around their router DNS. How good is your router DNS? Because that's going to give you a lot more information about Traceroute. It's in our best interest to do that. We have the networks. We want to help you troubleshoot them so you're not calling us all the time, or we have to troubleshoot them too. So we want to make sure we're getting accurate information when we run our trace routes, or when we ask you to run a trace route and send it to us. So it's actually really in our best interest to provide all this information. It's not just accurate router DNS, it's a bunch of other stuff that I'll talk about later. But if you think about it this way, if I've designed a really nice high performance car and I have one indicator on the dashboard that just says WTF, that's not going to be useful. I want to provide you with more information. If I built this great car, I should give you more information so you can figure out what's going on with the car as you're driving it. And there's a lot of aspects of what we embed in the router DNS that's actually really important. So one of them, of course, is we put location data there, right? Especially if you have a WAN. If you're going, across the country or across the state, you definitely want to have location data. And a lot of that is either SILI codes or IATA city codes. IATA is International Air Transport Association, which is basically the association of people who help you buy an airline ticket. So those codes are all really based on whether or not, where you can buy an airline ticket and with what destination and what source you're going to do. So that is useful to an extent. What's interesting about it is that people often use airport codes, but IATA also provides city codes for some of those cities where it's not coterminous with the airport. So for example, NYC is the city code for New York. A lot of people still use like LGA and JFK. And kind of what I figured is that people, and Toronto is really weird with this, where people used YYZ, which isn't even in Toronto. That's Lester B. Pearson Airport, which is in Mississauga. So it's not even like the same city, but and it's not close to a lot of the Toronto data centers. it sort of boils down to whatever I fly into is what I name the pop after. So I feel like that's kind of like what most network engineers do. The other way to do it other than IATA codes is silly codes, and then there's also just making it up, which is kind of what ESnet and Internet 2 do. But silly codes are sort of close to what we do, and so you get these kind of metro codes. The first four letters is actually the metro area, and then there's sort of like a region or state area that's given, state or province, it's given as the second part. So again, Toronto is a good one where the actual IATA city code is YTO, which very few people use. A lot of people either just make it up and say TOR, or they'll use YYZ, which is again highly inaccurate. YTC would even be better, but still, that's not the airport a lot of engineers fly into. So the other one I like here is silly codes only apply to North America. So people have sort of made up silly codes for other places. The one I love is London. It just looks like you've just typoed London. But a lot of people do use those first four letters. So they use the LOND part. And what ESnet and Internet 2 have done is kind of try to make some of the silly characters a little more readable. So instead of LSAN, we say LASA. I don't know if we got that from level three. If anyone else knows where that came up, because it's both Internet 2 and ESnet that did it. And it dates back about 15 or 20 years. So I'm not sure where we did that, but that's kind of what we're doing now with our router DNS. One of the things that Raz doesn't mention is that some people do link-based router DNS. Like this is the interface that goes to that router. So it's sort of a link-based DNS versus this is the interface that is Ethernet 305 on this router. A lot of people do interface. I happen to like interface-based DNS, but there are some reasons why you might want to do link-based. Okay, so if you look at this, I'm using an NLNOG ring node located at WashU in St. Louis. So NLNOG ring is very cool. If you don't know what it is, look it up. But ESN has a node on it. There's a few other nodes, UC Santa Cruz and a few other places. So if you want to know what it is, go ahead and look it up because it's pretty cool. And try to join it if you can. So what we're going to do is look at the router DNS and see what's happening here. So you can kind of see here, like WashU is probably doing interface space, and they're adding some information about the router and the location. That BIH is probably one of the buildings where it's going out of, and then CH1, that's Chicago. And then if you look at ESnet, it looks like it's link-based. This is kind of a funny Nokia-ism. It's actually interface-based, but it ends up being effectively link-based. And the reason is that Nokia router interfaces are actually named. So when you generate the logical router interface that it has the IP address, VLAN, and port tuple, that becomes a named object. And so essentially, this hop7 and this IP address represents the interface that's physically located on Kansas, which is in Kansas City, Kansas CR6. And that is the interface called DENV BBC, which is obviously the backbone link C, which is the third backbone link to Denver. So that gives you an idea of how we're doing DNS there, but it ends up looking like link-based DNS based on that. A little bit more involved, I traceroute to Berkeley, so we'll see a little bit more Internet 2 here. And you can see that Internet 2 has these 400 giggies, so it's obviously interface-based. Once we get to Scenic, though, you can see that Scenic has more link-based. This double dash thing I like, that shows you the link. I got the idea for our double dashes from Scenic, so that's why we have double dashes or double hyphens in ESnet. And you can see here Sunnyvale DC, which is one of Scenic's networks, to Sunnyvale HPR, which is another of Scenic's networks, and then you go Sunnyvale to Emeryville, and then Emeryville to UC Berkeley, et cetera, et cetera. I'm not looking at the chat. If anyone has questions, I don't know if you can raise your hand, but if anyone has immediate questions, feel free to raise your hand or jump in if you want.
It's just a little bit of chattering about the names of the cities right now.
Okay. Yeah, that always brings things up. ESnet, in addition to kind of like using the Internet 2 terms, and when you look back at those router DNSs, you'll see here CANS, DEN, SALT. You see in Internet 2 CANS, DEN, SALT. So it's basically taking the same path, and we're using the same naming scheme essentially. We also have a little bit in ESnet, we do a little bit more provider-based naming. So in some of the commercial providers like Equinix and Switch, we actually embed that in there. We're not totally consistent about it because we're kind of moving from one naming scheme to another. So really it's non-Lumen facilities, but also H5. We don't embed the H5 part. So we're in a couple of H5 facilities. So that's kind of, you'll see occasionally like Equinix SV5, we take their designation of the location plus something that, represents the vendor essentially. Okay, so that's DNS. Now let's talk about the RTT, the really difficult subject here, the elephant that's in the room, if you will. So RAS does a really good job of separating between actual latency and perceived, or I call it perceived, he calls it cosmetic latency. And there are three components that he identifies to actual latency, and that's serialization, propagation, and queuing, all of those delays. Serialization delay is essentially like how big the pipe is to force the bits into it. So it's like if you think you're drinking a cocktail, you're drinking out of one of those really thin, like stirring straws, it takes you a long time to drink. It goes slow. If you drink out of one of those big fat straws that you use for bubble tea, but you're drinking a cocktail out of that, you're basically chugging it. It goes really fast. So serialization delay depends on the size of the pipe. Propagation delay, of course, is the speed of light through glass, and queuing delay, which is the delay that happens in some cases with congestion, but it's whenever you have to queue the packet up for any reason in your router that will actually slow it down a little bit. And then we have a bunch of things that are cosmetic latency or perceived latency. So again, it's important to understand Traceroute does not attempt to measure, nor does it succeed in measuring actual latency. It doesn't measure the actual football field. It walks around the stadium. So it's possible to make some inferences about latency, but you have to be very careful how you do that. So the actual serialization delay on 100, so in terms of serialization delay, actual serialization delay on a 100 gig link is like a tenth of a microsecond, which means that 18-year-old Mike is going to tell you serialization delay is no longer a factor in modern RNE networks. Queuing delay may still be an issue, which would indicate congestion, potentially. That can indicate something else. And of course, this guy will tell you propagation delay is always going to be the same. It's going to be constant. Speed of light through glass is always speed of light through glass. The other important aspect that leads more toward cosmetic latency is the fact that modern routers do not handle ICMP responses the same way they handle forwarding plain packet forwarding. In other words, on modern routers, nothing like an 11750. So there's 11750 takes your packet, drops it, sends you back an ICMP. That's almost the same as forwarding it through the kernel, maybe a little bit more work. It's very different from what a modern router does nowadays. The modern router has very fast ASICs and very, very good processing for forwarding the packets, not so much for the ICMP. If you think about it this way, taking the expired food in the fridge analogy a little too far, if I'm cooking, I like cooking, I need to cook the dinner at a certain time. It needs to be done. It can't burn. It can't get cold. So if I'm in the middle of cooking and I take something out of the fridge, nice gourmet Parmesan cheese, shredded Parmesan cheese. Uh-oh, it's expired. Oh, and it's moldy too. I'm not going to take it down to the compost 8 floors down right then while I'm trying to cook dinner. I'm going to set it next to the compost bin on the counter, and I'm going to deal with it later. That's how routers handle expired packets, the same way that I handle expired food. Okay, so it's not going to prioritize sending you back your ICMP message so that your trace route has accurate times. It's just not going to prioritize that. So how do we understand actual versus cosmetic latency? One thing we can do is we can infer that if the latency jumps at a certain hop and it stays that way all the way through, this is one of the things Raz tells us is in his slides, you'll see if you can infer if it stays consistent across the single hop and then continues the rest of the way down in the path, then you can infer that there might be some actual latency. Except, what about the case of asymmetry? All right. That's not necessarily an example. I mean, it is actual latency in a way, but it's not because of congestion or because of a problem with a router. It's actually because of asymmetry, which is a different issue. It's still an important issue, but here's an example of asymmetry. All right, I'm going from ESnet, my host here right downstairs from where I am standing right now, a host called Joy Division, which is a Debian host, because why wouldn't I call it Joy Division if it's Debian? Um, and then I'm going to a host that I have in Los Angeles. It's a VM in Los Angeles. So you can see it takes a very nice direct path to San Jose and then goes on NTT's network and goes right from San Jose to Los Angeles. And then at some point, hop 11 here in NTT's network, we think all of a sudden the latency jumps from a very reasonable 10 milliseconds to a very unreasonable 70-ish milliseconds. What happened there? Well, clearly there's a problem in NTT's network. Clearly this router is broken, or there's congestion between these two hops or congestion between these two hops. And that might be an inference that people would make. That would be the wrong inference for two reasons. One is, first of all, this hop 11 probably isn't actually an NTT device. Just because it has an NTT IP address doesn't necessarily mean it's an NTT device and an NTT DNS name. Because remember, when service providers are providing services, they're like, I'm going to connect my router to your router. Here's the IP address you're going to use. I'll loan you the IP addresses from my stash of IP addresses, and you can just configure that. And then we'll set up the BGP session and set up our peering and all that stuff. So in this particular case, when you have this customer to peer relationship, they usually loan you the IP address since you're using their service. And that's probably what's happening. This device is actually probably a different provider's device or a different entity's device, the customer device here. And NTT is just doing router DNS for it and doing the IP address for it. And then you can see that latency continues all the way to the end. What is actually happening? The only real way, is Raz notes in his slides. He says the only real way you can tell is to go the other way. Go get on the other place and do a reverse trace route. You're going to see I'm going on to the other host now, and I'm going to do a reverse trace route. And you can see right off the bat, it goes to this provider called Atlantic Metro. And then it goes all the way to Washington, D.C. Now, the reason for that is Atlantic Metro prefers free settlement-free peering with ESnet, which back when Atlantic Metro was only Atlantic Metro, before they were apparently now Atlantic and Pacific Metro, we peered with them at Equinix DC. And you can see that it's still there. Equinix DC is where it goes over to ESnet. And you can see that peering relationship hasn't been updated. So it's a nice low-hanging fruit, something to do, but this is not based on congestion or based on any other kind of problem with the router. This is based on a peering issue and a path that's not quite right. So an asymmetry that's not quite right. The other one is MPLS. So I hope you didn't look when you saw these like router DNS examples I gave, you weren't looking at those latency numbers and seeing how weird they were. But if you look at this, we go from Washington U and St. Louis, and then we go up to Chicago, and then somewhere between Chicago and Kansas, we suddenly the millisecond jump by 40, 45, 50 milliseconds. And now we're all the way up at 52, and we pretty much stay that way all the way until we get to the name server, which again is right downstairs. Okay, so what's going on here? Does that mean that there's congestion right here at this part, but it stays pretty much the same? So that's an example of congestion. Well, let's see if that happens in Internet 2. Oh, wow, the same thing's happening in Internet 2 too. It's a little bit different in terms of the actual numbers, but as soon as we get from Chicago here to Chicago here, all of a sudden the latency jumps up by almost 60 milliseconds. What's going on there? Well, this has to do with how MPLS works. And remember, the original theory of MPLS is that you had provider edge routers and then you have provider routers. And the provider routers technically don't have to run routing protocols. They don't have to have any routes. They're just doing label switching. So MPLS could never trust that any router in the middle of the path actually knew the route back to the source. And when you get a TTL expired, you've got to drop the packet and then send an ICMP back to the source. So how are you going to do that if you don't have a route back to the source? Well, what MPLS actually specified is that you forward all the way to the far end. Okay. So you have to go, you basically take the packet out of the MPLS label, you put an ICMP packet into the MPLS label, and then you send it back down the way it's supposed to go with the same destination, the same label path that it had before, all the way to the end. And then the final router at the end will send back each ICMP TTL exceeded back the other way. So in other words, you're going to have latency that matches at every one of these hops. It's going to do that for every one of these hops. It's going to match the far end latency or the far end RTT. So that way you're going to see the RTT as soon as you hit router one, RTT for the far end, which basically means that you're going to see these numbers jump as soon as you get into an MPLS network. Okay, wait, I'm going the wrong way here. Let's go back. Also, the other thing to think about with MPLS is that it maintains its own TTL in the label stack. Many routers by default, when they encapsulate a packet in the MPLS header, they do the TTL. They create a new TTL, which is usually 255, and they forward it on. What that means is it's going to hide all of the intermediate hops because everything in between is going to decrement nicely the TTL, and that fake low TTL that your traceroute put in is going to get masked until it hits the end of the path. And then you're going to see at the egress point, you're going to see a hop. So every network, big WAN networks will have two hops in them in that situation. So you can also do something called TTL propagation, or sometimes called uniform TTL, where it copies the TTL of the IP packet into the MPLS header on ingress. And that makes traceroute work on a hop by hop basis, but it still gives you that wacky latency or round trip jump as soon as you hit the beginning. Now, why do we want to do TTL propagation versus not? Same thing is why we want to instrument our networks as well as we can. That's so our engineers, our NOC engineers, and our other, my colleagues understand, and even I understand, I can actually see the path that the packet is taking. I don't want to obfuscate that from me, and I don't want to obfuscate that from you. So it's in my best interest to turn on TTL propagation so you and I can both see what the trace route is doing. Now, one of the other reasons that you can't do immediate route back to, even if you do have full routing tables, even if all your routers are PE routers, they may be running different L3 VPNs. And the L3 VPN that they're running is not necessarily you're not necessarily going to know what it is. So what I'm trying to show you here is that in an L3 VPN, there are two ways that you designate the L3 VPN. One is you have a target community that puts the route in the correct VRF for that router. But the other is in order to know what packet, as a packet is getting received by a router, you want to know what packet what L3 VPN that packet is supposed to be in. You need a VPN label for that. That's an MPLS label that goes into the stack. So this is the VPN label for Joy Division. This is what it gets when it announces its route. It has a VPN label of 524.223. But I have a different host that's a Perf host on a different router. It has a different VPN label, but you'll notice it's the same L3 VPN because it's in the same VRF. So what Nokia does here is they ephemerally decide what the VPN label is going to be when they boot. They said, okay, this VPN is going to have this VPN label, and I'm going to announce that in every route for the BGP VPN family. That is useful for two things. We'll make some MPLS inferences a little bit later, but it's also useful to understand that no router in the middle is going to really understand what L3 VPN a packet belongs in. So it can't know that. That's one of the reasons why it has to send the packet all the way to the end. The router has to decapsulate it, put it in its L3 VPN, and say, oh, wait, now I need to send this all the way back. That's one of the reasons why you get that latency. So we just made two inferences regarding latency. One we made around asymmetry and one we made around the existence of an MPLS cloud. This had nothing to do with the actual latency. If anyone remembers this reference, I applaud you. But it's important to understand that we made inferences around latency that had nothing to do with latency. We made inferences around round trip time that had nothing to do with round trip time. So in other words, we walked around the stadium, determined how many seats were in the stadium, not the length of the football field necessarily. So we did have to verify that asymmetric path. Can we also verify MPLS using Traceroute? Yes, we can. that's actually really cool. That's a new innovation. Well, innovation is about 20 years old, probably, maybe a little older. And it started with NANOG Traceroute, and there are newer versions of Linux Traceroute and MTR. They often tend to use the E in order to that is to enable ICMP extensions, which are defined in RFC 4950. So essentially what happens is RFC 4950 specifies add more information into the ICMP packet that you're sending back, and that includes the MPLS label stack. So every ICMP packet you get that goes through an MPLS network has a label stack in it. And you can get Traceroute to parse that and show you what it is. So here we are going through Internet 2, taking the same traceroute, or maybe a slightly different traceroute. I'm going from UC Santa Cruz's NLNOG ring node to a Personar node in Xeon. Okay, and I'm going to see all of Internet 2's MPLS here. And so you see the labels, and we can make some inferences about these labels. For example, you see the label at the top is the same. It doesn't switch at each hop. And I'm giving you, this is MTR, I'm giving you slightly better format. It's a little easier to read. So you can see the MPLS labels are consistent, and you can also see that there are two labels. There's a top of stack and bottom of stack label. The top of stack label is consistent all the way through the path. What inference can we make from that? That's actually the very useful inference that Internet 2 is probably not doing any traffic engineering. They are doing shortest path routing between this ingress router and the egress router. So they're basically doing a loose shortest path. And it's probably segment routing that they're using, because that would not change the label. Segment routing uses the same label at each hop. If you're doing LDP or RSVP, you're going to do label swaps at each hop. You can also see here with MTR that we're starting to see some ECMP. Also another example that we're probably using segment routing, because segment routing is really the only signaling protocol for MPLS that is ECMP aware at the IGP layer. So you can make some inferences about this, that we're doing segment routing based on the label that we're seeing. Okay, now I'm going to show you ESnet. And it's a little wonkier, but it's still pretty much the same. You can see here again, there's one label at the top that stays the same all the way through. There's a label at the bottom that stays the same way all the way through. And then there's weird labels in the middle. What's up with the weird labels? The 7 and then some random label, literally random label after it. Exactly, that's an entropy label. So 7 is a label that says the next label, if you see a 7, the next label is going to be an entropy label. Why would you use entropy labels? It allows you to do better, more robust ECMP hashing. That's exactly why we're doing it. Okay. And then what's that final label? Remember this? I had my route for Joy Division has the VPN label, and then you can now see here's a trace route to Joy Division. You can see that the last label is in fact that bottom of stack label. That is the VPN label. So there's a lot of inferences we can make now just by using traceroute with the correct flags, using more modern traceroute than the classic ones. And we add some flags to it. And our networks, again, it's in their best interest to provide this information to us so we can actually see what's going on. So we know we're taking a shortest path, non-traffic engineered path. You notice this one changes. That's actually an artifact of some stuff that I'm doing in the network. We're actually running 2 IBGP meshes. I can talk about that later. So that's why you have these actually vary. They're not quite vary. It's still taking the shortest path. They point to the same router. So what about Tracepath? A lot of people use Tracepath, and one of my motivations actually is to talk about why I think Tracepath is not quite the tool you think it is. And part of the reason here is that Tracepath can show us that asymmetry. One of the things that it does do, one of the value adds that it provides, is it tries to guess asymmetry. And you can see it kind of does that in this very asymmetric path that I had, that I showed earlier. If I run Tracepath, it does show me the asymmetry. But it also shows a bunch of asymmetry in other situations where there's clearly not asymmetry. And you can see I've traced path between 2 Personar nodes in ESnet. You can see the path is the same. It's just the reverse of the previous path. I mean, in terms of the hops that it's actually taking, Houston to El Paso to San Diego to Los Angeles to Equinix San Jose. And then the other way around, it's Los Angeles to San Diego to El Paso to Houston to Atlanta. All right. So what's going on? Like why is it saying this is asymmetric? Well, it's the same thing that we just discussed. It's that ICMP TTL exceeded. The reason is that Tracepath tries to infer asymmetry by saying I set one as my TTL and I got back a packet with a TTL of 254. I sent two as my TTL and I got back a packet of TTL 253. That means the path is symmetric, right? But in the case of an MPLS network, when I send it all the way down to the end and then the TTL exceeded comes all the way back from that far end router, it's going to have a more decremented TTL at that point. So if I set the TTL at 2 and it goes all the way down to this router, it's going to come back with a TTL of like 251. That's going to look like an asymmetric path. Now, the one way you can probably tell that it's an MPLS based quote unquote asymmetry and not actual asymmetry is the asymmetry actually counts down here fairly consistently. And so that may be a way you can infer that this is really caused by asymmetry and not caused by sorry, this is not caused by asymmetry, but is actually caused by MPLS. All right, remember I said how RC 1812, not all vendors handle it the same way. Okay, so I'm going to show you some trace routes. This is a trace route that is from a Nokia router to another Nokia router using its loopback. This trace route is being routed using the IGP hop by hop. It's not using MPLS. And you can see what it's doing. It's actually very correctly hitting the ingress interfaces. You can also see some evidence of ECMP here, where there are multiple interfaces at each hop. But in this case, it goes to the interface from Equinix SV5. It hits the ingress interface at Sun CR6 that points toward Equinix SV5 and so on and so on. But when I trace route to something that is in an L3 VPN using MPLS as the forwarding plane, what happens? All of a sudden, I lose that ingress hop, and then everything else is kind of looks different. And then when I get to this router here, I see both sides of this /30 here. This is the /30 that Joy Division uses to connect directly to this router. So it's like, okay, what is going on? Why do I get both sides of the /30? And this also is true with IPv6. This is the same version with IPv6. I didn't do the loopback to IPv6, but you get the point. Okay, so this is actually what's happening. It's using the egress interface. So Equinix SV5 to Sun CR6, there's no ingress ICMP, and instead it sends the ICP response via the egress interface, and it goes all the way down egress here. And this egress interface, and then this Joy Division actually sends it from its own interface. That's why we see both sides of the /30. If I actually had a per sonar node, I do have a per sonar node connected. If I use that, it's even weirder because I get the ingress ICMP response from Equinix SV5, and then I miss this entire hop, and then I get this egress interface over here, and it goes all the way down. That's a case of where the router's actually following RFC 1812. And I think that's actually kind of a limitation in the way that Nokia's process MPLS ICMP TTL exceededs. It's actually documented, okay? And it also doesn't do ECMP. It doesn't actually show the ECMP next hop. So even though the packet forwarding is taking a ECMP, we have been able to determine that with NetFlow, it is taking the underlying ECMP. It's not showing it. So it's another example of how we're not seeing the actual path that packets are taking, even in a very modern router. Another example of that. This is where we have to make inferences that aren't necessarily based on what traceroute is telling us. Speaking of ECMP, ECMP is one of the hardest things to figure out in using traceroute. And there are a number of innovations that have been made that allow you to do better ECMP inference, better ECMP understanding. But it also gets really messy. Now, in the case of ESnet, if you've seen some of my other presentations, you've seen that I have done some segment routing stuff. that involves some parallel tunnels that do traffic engineering for transatlantic traffic from certain locations to certain other locations. And so when you are going from one of those locations to one of those locations and you're crossing the Atlantic, you're going to take a set of tunnels that are weighted ECMP. They are equal parallel tunnels, but they're all traffic engineered and they take completely different paths. So when you run traceroute on them or tracepath, it's going to get really messy. Or tracepath, it's not going to get messy. It's just going to lie. Okay, it's going to outright lie to you. But here is some of the messy stuff that you can create. This is a traceroute minus E to the CERN per sonar node from Joy Division, and you can see it goes all the way down. It's a lot of stuff to look at here. You've got a lot of MPLS labels. That's because again we're using segment routing, so you're going to see label stacks, and plus the entry labels, plus a bunch of other stuff. This is really hard to read, and so what we need to do is find tools that can help us read it a little bit better and also help us separate some of those ECMP paths. So again, if we wanted to use Tracepath, well, that looks easy to read. It just makes no sense. So let's look at it. We're going from LBL 59, which is the router that's right below me here, over to Slack, over to Stanford across the bay. And then for hop 3, we're suddenly going from the building next door. How did we get over from Stanford all the way back next door? And then we're going to Sacramento. Hop 4 makes sense, Sacramento to Salt Lake City. And then all of a sudden we're back in Sunnyvale. We just beamed over to Sunnyvale. And then we're going to Los Angeles to San Diego. And now we're going to Kansas City all of a sudden. We just beamed to Kansas City. There's no link between San Diego and Kansas City that's direct. You can see what's happening here, okay? There are ECMP paths that are being invoked at the different probes because each probe is separate. Each probe has separate source and destination port, which means it gets a different entropy label put on it. It gets hashed into a different set of tunnels. All of that stuff happens. And what happens here with Tracepath is it just sweeps all of that complexity under the rug and makes it impossible to really understand what's going on. Another reason why oftentimes people will send me a trace path and I'll say, can you send me a trace route, please, or an MTR or something else that I can do a little bit more inference about what's going on. So there are a few tools that will do this that are kind of cool. One is called Trippy. This is a fairly new tool, but it's in all the package managers for all of the operating systems I've used. It's in Brew, it's in Debian package manager, it's in FreeBSD ports, everywhere I've seen it. And it's written in Rust, so it's very portable. There is a little bit of interesting things about these label stacks. I don't think, like, for example, at hop 5, these two paths should not have the same label stack. So it's kind of doing something a little strange with that. I think it has to do with the way it's copying into and out of the data structure that it's using for those label stacks. But you can at least make some inferences here. You can see the traffic engineering that I'm doing in some cases. I'm actually taking basically taking a stack of labels, and one of the things I will tell you is the label space that ESnet uses. These that start with 420,000 essentially. These are all node SIDs, which means I'm saying take the loose path to that router and use ECMP underlying whenever you can. And then I'm saying here, if it's 390,000, that means I'm saying take a specific link. Usually that means take a specific link across the Atlantic. So it's pretty cool. It's still pretty complicated. By the way, I don't have a silver bullet here. The closest thing I have, I'll show you in a second, but it does at least reveal some of the complexity. You can start to make some inferences. Yeah, there's traffic engineering being done. There's multiple tunnels being used. Got it. It also gives you some percentage as to how often you're using those tunnels, which, given that I'm doing weighted ECMP, that's actually kind of useful. That actually gives you an idea. Is there weighted ECMP happening or is just regular ECMP? So there may be some things you can do with this. And Trippy also, the regular TUI has a graphing interface, so you can actually see different plots and different things that are going on. That's kind of cool. I only discovered this like 2 days ago. So if you've been using Trippy for a while and have some tips, let me know because I think it's kind of cool and I'm trying to learn more about it. Um, for ECMP, Dublin traceroute is also useful. It's kind of, like I said, I can't wait to see Harrisburg traceroute someday, but it's another capital city traceroute. Um, and it, as far as I can tell, can only do IPv4, unfortunately. And it produces really messy output. It's very detailed. It tries to decode the ICMP, RFC 4950 ICMP very extensively. So it shows you the label, it shows you what the experimental bits say, et cetera, et cetera. Experimental bits in ESnet, those are used for type of service or quality of service. In most cases, zero just means best effort in profile. So if we go here, it actually has a nice JSON output as well. So you can do your own parsing of this. So that's actually really cool. You can parse this and present all the format, columns and graph it the way you want to and do all that stuff. That's awesome. The only problem here is that it's still only IPv4. You're not seeing any IPv6s. So we need to bring Dublin traceroute into the current century, basically. So the one that I think is maybe kind of useful for interactive visualization of ECMP paths is called ETR. That's written in Go. And I have a video of it because it shows you how you interact with it. But what it does is up top, it gives you like a hash of each path. You can page through each of those paths that it's showing you, and it's showing you the full set of paths. You can see that they take different directions. Sometimes the paths are repeated because, again, I'm using weighted ECMP here. And let's run it again just so you can see it. The paths are repeated. So this like A5CE86, that reappears because, again, I'm doing weighted ECMP. So some of the paths are going to happen more often than others. But it does give you a pretty good idea of how many unique paths are out there. You have to kind of pad them out, like basically try to do like 20 paths instead of 10 and try to figure out, how many unique paths you can find. We use this to troubleshoot a problem with a customer going to Microsoft, actually. We were able to see that they were doing a lot of ECMP inside of Microsoft's network. That was kind of cool to do. And we were able to use this tool. It's available on GitHub. I have a reference of it later. And it does have, you have to do custom repos or download their repo and put it into your own homebrew or whatever you're going to do, wherever you're going to use this. So anyway, I think it's a really cool tool because ECMP is one of the things we do a lot of, and it's one of the things that's hard in regular traceroute, and it's impossible in Tracepath. So I do a little bit of a matrix. This obviously isn't done, and I'm kind of take some input. I'm not sure if I'm ready to like maintain this in the same way that like Warner maintained his switch queuing buffering for all those years. But it's kind of useful to have this because there's such a weird Venn diagram around like what you need to do if you want to see those MPLS labels, or if you want to see ECMP awareness, or if you want to see PMTU discovery. And the thing that about Tracepath, one of the things that sort of benefited people was to be able to use it for PMTU discovery, but you can also use regular Linux traceroute for that. So uh, it doesn't present it as prominently as Tracepath does, and it doesn't do it by default. You have to say minus minus MTU, but it will do it, and it will get you the correct results, or it will get you, I think, reasonably accurate results in terms of where the PMTU changes or where the MTU changes on a particular path. Okay, this doesn't even have all the tools. I didn't put Dublin traceroute in here because, of course, it doesn't have IPv6, so it should be disqualified. But there's also Dublin traceroute, and there's also Trippy, which again I just discovered recently. So I haven't even figured out all the things it can and can't do. Modern networks are complex, and the way Traceroute interacts with them is odd. It is not immediately intuitive how to understand that. I hope the examples that I've given here, launching from a more generalized tutorial of Traceroute, have given you an idea of how you can still make really useful inferences, but they're not immediately available on the surface to your intuition. I've also, one of the things I kind of wanted to do here is kind of point out a lot of people use Tracepath. It's not quite as useful as you think. Let's see if young Mike has anything to say. Not really. He never did. If you have any questions, let me know. Here are the references. I think we have 3 minutes for questions.
All right, thank you, Michael, for going through all of that. Everybody is unmutable, so if anybody wants to raise your hand or unmute and ask a question, please do so. And while we're doing that, I can just replay what was in the chat room here. There was some discussions about the city codes. Michael Lambert was talking about ICAO rather than IATA codes. And Rune was pointing out a talk about actually trying to create a map of physical locations.
Yeah, I was going to point that out, and I just skipped it in the interest of time. But I've never seen anyone use iCal codes. So there are no EGLLs in there or anything like that. And I don't think they have city codes either. So I don't know if iCal has a city code. So yeah, if you had your London data center, it would have to be like EGLL or one of those like that. It's easy in US and Canada because you just add a K or a C to the regular airport code, but like, I should say continental US and Canada, or lower 48 in Canada, but there are other things that change. But yeah, iCal is an interesting one. Go ahead, Michael.
Okay, so the ICAO code, the hospital next to our data center has a helipad which has an ICAO code. So we were tempted, why not use that?
Yeah, that's good. It may have a 3-letter code also. We don't know. But yeah, if it has an ICAO code, yeah, that you could use that, I'm sure. Um, the reason I don't think anyone's used it is because they're kind of obscure. Like again, where's EGLL? Where's PHOG? They're not immediately available to people other than pilots in terms of intuition. So that's I think kind of the reason I don't see people using them quite as much.
Okay.
The other thing on campuses, we use a lot of building abbreviations, and because otherwise I'd have, 40 routers that are all MPLS.
Yeah. If you go like back to one of these that I did, you have to kind of know, like I actually looked on the map at, what's it, this one here? Let's do this one. I actually looked on the map. There's such a thing as Bixby Hall, but it's a really old building. So I'm not sure if they put a vault near Bixby Hall that has a modern router in it or what, or they just, when they restored that building, they put a really nice data closet in there. I'm not sure. But I don't know what else BIH would be. I looked on the map at WashU, and that's the only one I could think that made sense. And then here, these I know because I'm like right near campus, but that's Sutargia Die Hall, that's Earl Warren Data Center. Like I know where a lot of that stuff is.
Yeah.
But you have to kind of know the campus. Yeah.
Yeah, exactly.
Good point.
I like the double dashes though. I'm gonna steal that.
Yeah, that again, the credit where credit due. That innovation came from Scenic.
Yep.
So you can see that looks like UC Berkeley picked it up, and it looks like and we in ESnet have picked it up too. So I know I got it from Scenic. So
All right, and then last thing is that Eric was noting in the chat room, various trace tools get passed or don't get past NAT, and the different terminating conditions are used by different trace tools.
yeah. Yeah, that's a good point. There were only so many things I could include in this in 1 hour. So
or in summary, NAT is evil.
yeah, that's true.
There we go. That's a good note to end on. Does anybody have any other questions? All right. Well, thank you so much, Michael. If you want to shoot me a copy of your slides, I'll make sure they get posted with the video. And next week's talk is Fabio Andriakis from SDSC, and he's going to be talking about OSDF and ESnet. So we'll talk to everybody next week. Hope everybody has a good weekend.
Thank you all.